Well, hello everybody. This is going to be homework number 1. I'm going to be using an example from some research that I've done in the past. So I'm going to explain a little bit what this research is, but the whole goal of this homework is to get you oriented to how to use COMSOL multiphysics and how to find things in the menu. So as you can see on the screen right now, this is our final product, and I'm going to show you how to get to this final product. The problem that I'm referring to is shown here in the picture. This experiment is done with cells grown in culture. These are endothelial cells, and these cells are about 30 microns or so wide, and they are high in the middle and low on the sides. The way that this experiment works, so the goal of this experiment is to find how quickly lipid molecules move around the surface of the cell, so how they move through the membrane. And it's called fluorescence recovery after photobleaching, or FRAP, F-R-A-P. And the way it works is that you stain the membrane, and then you take a section of the membrane and you photobleach it. Photobleaching means shining a high-powered laser at the area, so that part of the membrane is not fluorescent, and the other parts of the membrane are fluorescent. And then what you do is you take a line, I can draw that line, and you monitor the fluorescence across that line. So if you can see this line okay, let me just make it a little bit bigger. And just change the color. So you monitor the fluorescence across this line, and what happens is that molecules move from the outside of this area to the inside, and bleached molecules move from the inside to the outside. So as you can imagine, the bleached area goes from being dark to light, and then the outside area a little bit goes from being light to a little bit darker. Okay. So this is described by the diffusion equation, and I don't have the equation here, but we'll see it when we go to COMSOL multiphysics. But if we plot the results from the diffusion equation, we get something like this, where we've normalized the concentration here. So the concentration we're saying is 1, but it started at 0 in the middle and 1. So it started at 1 on the outside of the area, out here, 0 in the middle, which is here, and 1 on this other side, which is here. So as time goes by, as I mentioned, things move into the bleached area and out of the bleached area, so the fluorescence in the middle starts to recover, and we get a concentration increase in the middle and a slight decrease on the edges here. Okay. So if we look at this problem, in this case we've said that the bleached area goes from minus 0.25 microns to plus 0.25 microns, and the non-bleached area is outside of that. In the problem that I'm going to do, I'm just going to make it simple and make this a 5 microns, 1 micron, and 5 microns. So it'll be a little bit different than what's shown here. Okay, so let's go over to COMSOL multiphysics, and as you can see, this is the final result that we're looking at. And the way that we got this result was to make the concentration 1 on the outside, 0 on the inside, and then 1 on the outside again. And then we program this to obey Fick's law of diffusion, and as such we have an increase in concentration in the middle and a slight decrease on the edges, like we saw in the experiment. So to take a look at the structure of COMSOL multiphysics, what we have here is a model that is defined by a particular geometry. There are particular materials. There's a particular physics that's used here, in this case transport of dilute species, convection and diffusion, and as you know, we're going to set convection to 1. There's values at nodes and so on, initial values. And then there's something called a mesh, and a mesh is how we divide up the problem to small sizes and then let the computer take over, and we can define the areas of that mesh. Then there's something called a study, and a study basically says, do we want this to be time dependent or not? And then we have a results section, gives us the results, and we can look at things like concentration or whatever else that we've programmed in here. And then we have something called a report, and a report is this output. So if we wanted to send this to a file, we would maybe make an animation or a movie or so on and so on. Okay. So what I'm going to do now is to start a new one to show you how I got to this point. Okay. So I'm just going to click on New. So this is going to be a 1D problem, one-dimensional, okay, because it's just going to be on a line, is how we're going to define it. So I'm going to click on 1D, and as you can see here, under this model wizard, I have these next arrows, just like setting up any kind of program. So I have, back, next, and finish, and this model wizard only gets us so far, and you'll see in a second how far it gets us. So as you can see, I recently used this transport of diluted species, but I'm going to just show you exactly where that is. It's under chemical species transport, transport of the diluted species. So I highlight that, and then I click next, and now I've added that as my physics. And as you probably know by now, we can add multiple physics and make them interrelated. So I have the opportunity now to put these preset studies. So I want this one to be time dependent so I can see the recovery of the fluorescence. And as you can see, we don't have another next. So I click on finish, and then I'm brought to this screen. Okay. So what you can see is that we now have, I haven't saved it yet, so it's untitled. We have a model 1, definitions, geometry, materials, and then our physics and what's called a mesh, and the study and results. Okay. So I'll be going through each one of these and showing you what we're going to be doing. So in order to define the geometry, when I click on this, I see our unit lengths, our meters. We just have to keep that in mind because we're going to enter microns as e to the minus 6. Not worried about degrees right now, and we can keep our default settings here. So you also see you have these down arrows. Those give us some other things. If we had multiple things that we drew, we can form a union. But what I'm going to do is right-click on geometry, and I'm going to create an interval. So in 1D problems, as you probably know, we can only have points and lines. So we're going to put that one in, and number of intervals could be 1, but we're going to have 3, so I'm going to click on many, and I'm going to put my points in as 0, 1, 5 e to the minus 6, that gives us at 5 microns, then 6 e to the minus 6, that gets us that 1 micron in the middle, and 11 e to the minus 6, that gives us another 5 microns on the right hand side. Okay. So up here we see we have build selected, build all. Build all will change everything in the model. Generally speaking, let's just do build selected for now. That just means it updates what we just entered. Okay. Unfortunately, it doesn't show exactly what we did. So we're going to, but we'll see that in a minute. Okay. I'm not going to worry about materials right now because we're going to just define a diffusion coefficient. We're going to go straight to transport of diluted species, and as you can see, we have these domains here: domain 1, 2, and 3. 2 is going to be our bleached area. So here's domains 1, 2, and 3. Number of other things you have here. You can add domains if they didn't occur here. Right now, all the domains are. If you want to do manual, you could just add 1 if you want to do that. We're going to deselect convection. We're not having convection in here. Okay, and so if we click on look at our dependent variables, the dependent variables are concentration. Okay, and as we click here, we can see that our domains get highlighted. Alternatively, we can also click over here, and we can see that they're highlighted over here. So you can go either way. Okay, so we need to define an initial condition. Okay, so I'm going to right-click on my transport of diluted species and look for initial values. Okay, the initial values are going to be 1 here, 0 here, and 1 there. Okay, so what I'm going to do is add 1 and add that. Change that to 1. I may need to add a second. Okay. What I wanted to point out that I forgot to is that the initial values were already shown here. Okay, so let me go back. I'm going to delete these just to show you what we can do here. So clicking on this down arrow could also show us our initial values. So the initial value for click on initial values here. Initial values for 1, 2, and 3, the default is 0. So I'm going to make those 1. But we want the initial value in the middle to be 0, and we can't change that in this one. We have to add another initial value. So we do that by having initial values 2. And what we do is we click on our domain 2, add that, highlight it, and now we have our 0. Okay. So what you'll see is if we go back to initial value 1, we've overridden this one, and so we'll have all 3 there. Okay. So that's a little cumbersome, but you can just keep adding initial values if you had other ones that you needed to do. Okay. So in terms of meshing divides up the problem into small elements, and we normally would start with a normal mesh, and so we'll just do that, and we can build that. And again, unfortunately for this, I'm not sure why, but it doesn't show us our initial mesh. It will show it a little bit later. Okay, so we can go down to our study. Our study means, what exactly is it that we are going to be looking at. If we go back to our FRAP picture, okay, then we see that we should expect recovery in on the order of 1 second according to this model. Okay, so that actually helps us. Here we have 0.1 and 1. I happen to know that we might want a little bit more resolution in the time. So what this is, it gives us our start at 0, our finish at 1, and it gives us 0.01 second increments that it's going to solve. So it's going to solve all of those increments. Okay. So I think that that's just about it. We can now click on study. We could either right click and compute, okay, or we can just hit the equal sign here and compute it. Okay. So what you can see is it's plotting, and this is our first plot. So a few things that you have here are all of the times. So you can see it's 0.01 increments from 0 all the way up to 1. So since they're highlighted, you can see that means that they're all being shown over here. If we wanted to, we can do shift and then just select them all. You can control click them. I'm doing shift with the down arrow and then just getting them all. So what you can see here is it shows the first solved value, and you can see it's sort of rough here, okay? And that's because the number of elements that I chose were not really sufficient to solve this very well. The other thing you can see here is that the recovery went from this value very quickly to this value, probably in the first 0.01 seconds. And that's likely because the diffusion coefficient was very high. In fact, I did not set that diffusion coefficient. So in order to set the diffusion coefficient, I go into diffusion, and I see that it's 1 e to the minus 9 meters squared per second. It really should be a little bit faster than that. So I'm going to put 1 e, it should be a little bit slower than that, 1 e to the minus 14. I think it's about 5 orders of magnitude. But we can always just check this by going to study and then equals again. So every time we change something, we're going to see it. So that was a little bit too slow, because you can see it didn't recover at all. So let's go to diffusion again, and let me just put something, sort of in the middle here, and go to study and solve again. Okay, so we're starting to get close to what we've seen. As you can see, we probably want to be a little bit more rigorous in defining our diffusion coefficient, but in any event, hopefully you get the idea. So, but this is still very not smooth. So in order to fix that, I'm going to fix the size of the mesh. The maximum element size right now is e to the minus 7. So let me make that a little bit smaller, and e to the minus 8. So that's 10 times smaller. You can see our mesh elements here are shown there. And now if we remesh that, but we can still go back to our study, push equals again, and now we get a much nicer result. So the last thing that I'd like to show you in this example is under report. I can go down to report, and I can do an animation. Okay, so an animation is going to show us all of this as time goes. To show the animation, I have this animation, and I basically just click export. Ultimately, I can export this to a movie, but export will just at least show it in this window. It takes a little bit. And we'll be doing some other problems the same way. Enjoy.